Hello, I'm very happy to be here today. I'm going to talk about BERT, the NLP neural network that was probably mentioned a few times here today. I'm going to focus on how we can make it know and reason a little bit more like a doctor. So a little bit about me. I'm Rachel Wittis. I work as an NLP data scientist at Zebra Medical. I hold a master's degree from BIU NLP lab in Bar Ilan. And for the past few years, I've been learning to understand how doctors think and how we can teach algorithms to understand them. A small story. A year ago, I took a head CT scan. And a few days later, I got a radiology report interpreting the scan written by the radiologist who reviewed my scan. Now, I don't have any official medical training, but in the past few years, as part of my work at Zebra, I read a few thousand of radiology reports. So at this point, I like to play a game I call How Long Before Calling a Real Doctor? How much of the report I can understand myself before I get to the point where I need advice from someone with actual medical training. So the beginning was easy. Unremarkable is a good word. You want to have it on your report. Also normal, great word. No evidence of, amazing. Mass here means tumor. The radiologists have a lot of words to describe tumor or suspicious to a tumor. And metastasis, neoplasia, mass, cavitation, malignancy, and so on. The one word they will never use is tumor. So no evidence of mass is great. And then I got to this sentence, retention cyst in right maxillary sinus, and I got stuck because I never met this term before. So I called a radiologist, and he told me that it's actually a good type of rare. It's a finding that is so insignificant that it's often not mentioned in the report, and this is why I wasn't familiar with it. So what we're going to talk about today is how BERT would do in this game. We'll see that it's prone to the same mistakes that I would do as a person who sees a lot of reports but doesn't have a lot of medical knowledge. So this is the agenda for today. We're going to talk about medical blind spots that BERT has. We're going to talk about medical ontologies and lexicons, and I'm going to explain a little bit about why doctors like them and why they created them. And we're going to do some BERTology. We're going to open up and review a few algorithms that were created in order to inject medical knowledge into BERT. So let's start. BERT blind spots. BERT is a very popular and successful algorithm, part of a group of NLP algorithms called pre-trained language model. The basic idea is this: we first train the model very heavily on a very large corpus of non-annotated free language data. And in the next step, we fine-tune it on a small amount of labeled data specific to the task that we want to perform. These algorithms prove to achieve great performance. They are very popular. One very strong advantage they have is that they don't require a lot of annotated data, which is amazing for the medical domain. Of course, we want the data to be as close as possible to the data in the task we're performing. So in the medical case, we would like to pre-train it on medical text, which exactly what happened a very short time after BERT was published. We got BioBERT pre-trained on PubMed and PMC data, and then we got clinical BERT pre-trained on PubMed and PMC and Mimic. Mimic is a data set of clinical records. And then we got BlueBERT even more strongly trained on PubMed and Mimic. And all of these prove to have a better performance on medical text than general BERT. But is it enough? Does just exposing BERT to more and more medical text will teach BERT medicine? Or would it still be missing something? In the past 2 years after BERT was published, there was a lot of research done on what does it actually know and what are its blind spots. And it turns out that although language models capture a lot of knowledge, they still have gaps with knowledge which is not explicitly stated in the text. This is in the picture, it's Professor Catherine Abbasi speaking in a conference that was held a year ago, back when we used to have a live audience in conferences. And she talks here about our knowledge of what would happen if a giraffe walked into a room. We, as people, can imagine more or less how a giraffe would feel, how we would feel. But this type of knowledge is something that BERT has a blind spot for. It never actually met a text talking about a giraffe walking into an auditorium. So this was an example that Professor Catherine Havasi gave for knowledge that BERT wouldn't have just from being exposed to a lot of text. Do we have such giraffes in the healthcare domain? So it turns out we have, and quite a lot. First of all, clinical records have a lot of underlying medical knowledge, which the doctor uses to write the report, but he doesn't or she doesn't explicitly state it in the report. Here's an example from the radiology reports. The reason the person came to do the scan, the indication or history, is very important for the radiologist to understand what he or she are looking for. And it will affect very much the finding section of which finding they found. But this is not stated explicitly in the report in any way. This is an underlying knowledge that the BERT would never be exposed to. Another phenomenon we have in the medical domain is what I like to call the all happy families effect. Based on the famous sentence from Anna Karenina, happy families are all alike, and unhappy families are unhappy on its own way. So we actually see the same phenomenon in medical records. The happy sentences, the sentences stating that everything is normal, there is no that, there is no this, are all formulated in a similar way, and they are very, very frequent. The unhappy sentences, the sentences that actually discuss some kinds of problem that was found, some kind of finding, this all will be unique because they would usually describe the location, the size, and so on. So they will be unique and they will also be rare. And what happens is that when BERT is exposed to a lot of text, he actually sees a lot of the happy sentences and a small amount of the unhappy sentences, which are actually more important to it in order to understand medicine. So this is another giraffe, another blind spot we have in our domain. And the last problem we have, it's not specific to medical domain, but it is a problem that we have more than other domains, is the lack of label data. The way BERT works is that we can compensate if we don't have certain knowledge in the pre-training. We can later inject this knowledge in the fine-tune stage using a specific task to this knowledge. But in the medical domain, we don't have a lot of label data for such tasks. It's because of confidentiality, because it requires a very high level of expertise to annotate medical text, and because the medical language actually consists of many different sub-languages for different types of records. So you need to annotate a lot more data. So because of all of these problems, we don't have enough label data. But what we do have, we have one very strong advantage in the healthcare domain. We have a vast amount of very rich and manually crafted medical ontologies and lexicons. What are those? So doctors have many words for tumor, and computer science people have many words for structured knowledge databases. Ontology, knowledge base, lexical database, knowledge graph, semantic graph, and so on. But the basic idea is the same. We have entities representing entities in the real world, and we have relations connecting those entities. One very common connection is the one very common relation is the is-a relation, indicating a parent-child. Bronchopneumonia is a type of pneumonia. Pneumonia is a type of airway disease. You would always have this in your medical ontology, and you would almost always have also the same as relation, the synonyms, other ways to say the same word. And then in different ontologies, you see different types of other kinds of relations. For example, at site, pneumonia appears in the lungs, or may be treated by. Pneumonia may be treated by acetylcysteine, and so on. These are two examples for very famous medical ontologies. One is the UMLS that was created in the 1980s. It contains more than 1 million concepts and dozens of different relations. The other one is a little bit more focused. RadLex is focused to the radiology domain, and it creates a little bit, it contains 45,000 concepts. Why doctors love ontologies? Why did they manually craft them? One important goal of ontologies for doctors is standardization. I once reviewed a radiology report with a doctor, a radiologist working in Zebra, and he told me, I will bet you anything that this report was written by this and this doctor from this and this institute. And of course, no need to say all our data is properly anonymized. So I asked him, how did he know? And he said, well, he uses here this Hebrew biblical term for atelectasis. It's pronounced sircha, that only he uses. He's known for being the only person in Israel for using this term for atelectasis. So this is how I know. So it's not always that extreme, but different doctors do have different preferences regarding vocabulary, and they have them for a reason. Those different words for tumor that I showed you, if you ask a radiologist, he will explain you what are the differences between them, why he prefers this word and not that, why in a certain scenario, it will be incorrect to use one of them. But in the end, good communication is the most important thing for doctors. If they found out a finding and they didn't communicate it well, it's worse, or not worse, but it's the same as if they didn't find it. And some degree of standardization is very important for good communication. This paper you see here, Radiology Reporting from Hemingway to Hull, was written by a radiologist 3 years ago. I advise very much for people dealing with radiology text to read it. And what it states here, it's basically in the title. He said that it's very nice to have very semantically rich and nicely written radiology reports like Hemingway, but it's more efficient for communication and for the medical community that doctors write more like Hal, more standardized, more good for automation. And for it was actually proven that the communication is way better if you write in a standardized and structured way. So some lexicons like RadLex were intentionally created as guidelines for doctors to which terms to use and which not, and others are just suggested for doctors to have good communication and standardization for their reports. Another reason doctors love ontologies is because the representation of importance and severity of terms there is better than in free text. We talked before about the all happy families phenomenon, where the important or rare findings weren't adequately represented. So what happens is ontologies is the most of the ontology is focused on the area of the rare findings or the important finding. Each finding will be represented in respect to how important it is, how many synonyms it has, how many subtypes it has, and not according to its prevalence in free text records, which might be misleading. And the last reason doctors like ontologies is because it enables healthcare digitalization. Doctors have an unjustified reputation of opposing to automation and digitalization of any sort. But in fact, as early as the 1980s, these ontologies were created by doctors because they anticipated and they were eager to have more automation in their domain. They understood it can save them a lot of time and effort. And the reason they did ontologies is because they assumed that structured knowledge will be easier for computers to process than free text. And partially they were right. We would expect that ontologies and neural networks will nicely cooperate with each other. But what actually happened is that while the medical field was moving towards structured data and standardization, neural networks moved in the opposite directions toward processing and training on free text because this is what we had available. So today it's not so trivial to use structured data in a neural network setting. And now we're going to see a few algorithms who found different ways to do it. Some BERTology now. Let's start from UMLS BERT. This guy is regular Joe. This is the regular BERT algorithm. Regular BERT algorithm receives three types of embeddings in input. The token embedding representing the token, the segment embedding represented the sentence segment, and the position embedding encoding the position inside the sentence. What happens in UMLS BERT when regular Joe goes to med school is that we're adding another layer, this blue layer you see here. This is the semantic group of the token in UMLS. UMLS semantic group is the highest layer of the UMLS hierarchy, and it contains general concepts like anatomy, disorder, treatment, and so on. And what happens here now is that when BERT meets a rare term that it didn't see during pre-training, it already knows something about it. For example, here, plural effusion, even if it wasn't seen on pre-training, BERT would know that this is a type of disorder. Another thing that is changed in UMLS BERT is in the pre-training, the part of predicting the masked word. BERT is trained on masking one word in the sentence and predicting it. For example, here we mask the word dog, and BERT is pre-training by predicting this missing word. What happens in UMLS BERT is that we allow BERT to also predict the synonyms of the masked word. For example, here, if we masked lung, BERT could predict instead pulmonary or lungs, and it will still be correct, because those are synonyms of the word lung in UMLS. And this again allows BERT to gain information about rare terms. And what we can see here is that when we ask different types of BERT to predict words most similar to different medical terms like heart, kidneys, mass, we see that instead of predicting common words that are not necessarily clinically related, like BioBERT that predicts liver for heart or weight for mass, UMLS BERT actually predicts more rare words that have a very strong clinical relation to the medical terms like heartbeat for heart or lump for mass. So the reason I really like UMLS BERT is that it's very simple. It does a very small change in BERT and already gives BERT more knowledge than it had, and in not very specific or complicated way. But now let's see a more complicated algorithm, the clinical KB Albert. So as we said before, BERT is pre-trained on predicting masked word in a sentence. This is regular BERT. And it's also pre-trained on another task. It receives two sentences and it needs to predict whether they appear next to each other. For example, here, my dog is cute and he likes playing would appear together. And this is why it needs to predict that in this case, they are next. What is done in clinical KB Albert is another pre-training task. Instead of inputting a sentence, we input a triplet of two entities and a relation. For example, here it's pneumonia and acetylcysteine, and the relation between them is may be treated by. And we let BERT predict whether this triplet appears or exists or doesn't exist in the ontology. And in this way, we inject into BERT not only knowledge about the terms that appear in the sentences that we're going to train or test him on, but all relevant knowledge covered by the ontology. We can use here and pre-train him on all the different triplets in the ontology. And it also gains a deep understanding of the different relations meaning. So this algorithm deals not only with the problem of rare words or sentences, but also with the underlying medical knowledge that isn't mentioned in any way in the text. And moving to yet more complicated structures, there are two very famous algorithms for injecting structured knowledge into BERT, ERNIE and NoBERT. They weren't created specifically for the medical domain, but they were designed to deal with any structured knowledge containing entities and terms. And both algorithms relied on knowledge-based embeddings that were created based on the knowledge graph structure by itself without the sentence. And then the architecture here is of recognizing mentions of these entities in text and concatenating the knowledge graph embeddings with the contextual embeddings coming from the sentence. So that BERT gains both the knowledge from the sentence and from the knowledge graph. Part of the challenge that NoBERT deals with is entity disambiguation. You can see in this example that the sentence mentions purple rain, and it's important to disambiguate whether it means the album, the film, or the song. This is actually less of a challenge in medical ontologies. But nevertheless, we can get our medical knowledge into BERT just by using those systems with medical ontologies as our knowledge graph. And I saved my favorite algorithm for last. So far, we injected structured data into BERT by rewriting it in different ways so it can read structured knowledge, even changing its architecture. But as we said before, BERT is originally designed and intended for free text. What if we could somehow translate our structured knowledge into a free text task that BERT could fine-tune on this? This would be a very BERT-wise way to teach BERT. Instead of changing BERT, we could play on its strengths. So how is it done? This is one example from a paper that is actually not medically related. They start from ConceptNet. It's a knowledge graph representing common sense knowledge, like that city has a population. So they start from the triplets of the knowledge graph, and then they use Wikipedia to find a free text sentence in which this common sense knowledge appears. For example, the largest city by population is Birmingham. In this sentence, we can actually see the entities of population city and the relation between them. That city has a population. And then the task would be this, the sentence from Wikipedia. Inside it, we're going to mask one of the entities, and BERT needs to figure out of a few options, what is the masked entity. And note that it's more confusing than just memorizing all the triplets in ConceptNet, because all three answers here actually have some kind of relation with location. But only one of them has a relation with the location of a city, which is mentioned here, which is actually masked here. So it's not very easy, and it actually makes BERT deeply understand the different concepts and their relations using free text. And there's a somewhat similar idea is introduced in this paper, infusing disease knowledge into BERT in the medical domain. So here they start from MeSH. MeSH is one of the oldest medical ontologies. It was created in the 1960s, and it is still used to index medical records. And it actually had a printed version up until 2007. And they also use here Wikipedia, but this time not only as a free text, but also as a semi-structured knowledge source. Due to its structured nature. We have in Wikipedia the titles, the subtitles. It's a semi-structured knowledge source. So what do they do? The idea is to create many question-answer paragraphs in this template. What is the aspect of disease, and a free language answer. So the disease name is taken from MeSH and Wikipedia title. The concept, the aspect like diagnosis or cause or treatment are taken from the different subtitles in the disease entry in Wikipedia. And the answer to the questions comes from the paragraph under the aspect subtitle. For example, here under diagnosis in Wikipedia, it says the standard method of testing and so on. And this would be our free text answer to the question. So in this automatic method, they acquired 14,000 QA pairs, about almost 6,000 diseases, and they pre-trained BERT on predicting mask words in these paragraphs. And what they show in the results is that BERT improved not only on question answering tasks, it also improved on medical language inference tasks. Medical language inference tasks are tasks when the algorithm gets as input two sentences, and it needs to decide, it needs to reason logically whether one of them is entailed by the other. It actually requires reasoning that a doctor would do in this case. So the fact that BERT improved also on this task means that the knowledge was really infused inside the language model. And it also improved on disease name recognition. So this method is more similar to how medical students learn, by reading and writing text and answering questions instead of just processing structured knowledge. And I also like it because it's more organic to how BERT works and to how BERT actually learns its language model on the free text. So in summary, what we saw here today is pre-training on medical text is not enough. BERT will still need to acquire a lot of knowledge that is not explicitly stated in the text. We saw that ontologies better represent importance of medical terms than free text, and more similar probably to how doctors perceive them. And we saw that BERT can digest ontologies and probably beat me in the how long before calling a real doctor game. Thank you very much. It was a big honor to speak here today. And if you're also interested in making algorithms think more like a doctor, I'll be happy to hear from you.